All right. Good evening, everyone. This is Celso Batali, Astronomy 10, Evergreen Valley College. And I'm starting again because I didn't have my microphone on. So, as I always do, I would like to show what is going on as far as mandatory assessment is concerned. We have a homework based on Earth and its geology that is due on July 9, which is Monday. And pretty much that's it. And we have a somehow is not indicated here, but I should have another discussion on that week. I would check that. I would imagine there would be another discussion opening up next week, but I can't see it. Yeah, see July 7. I should have another discussion initiated on Monday. It might be in assessments, but it's not there in modules. Let me check that quickly. This is the discussion we are doing now. Oh yeah, I don't have a discussion set between now and next week. So yeah, take a break on discussion. Take a break on discussion. So next week discussion is none. Okay, so we have then, that seems to be a relaxing week for all of us. So no discussion and um, but we have this homework on Earth geology. Today in the chat, I will create a new extra credit. I'll show you in a second. And there is another extra credit, Bad Astronomy Everywhere. This is an interesting thing. So if you see a picture or some story that indicate bad astronomy, describe that and show the picture to prove. Not only describe, but picture. For instance, with the moon phase, you have a lot. There are restaurants that show a picture of the moon in a completely weird phase that is totally impossible. There is a wine that uh, I saw the label in Safeway it was in the spring when I saw that. It's called Fireflies, and the label astronomically makes no sense. So if you have that, upload up to July 10, and then you have some extra credit there to go. Um, so it's, as I said, it's a nice, easy few days ahead of us. Okay, so as far as Earth, planet Earth, on Monday we saw that because of the solar heat, because of the solar heat, the inner planets, Mercury, Venus, Earth, Mars, and also the asteroids and satellites like Moon, Phobos and Deimos in Mars, these objects are rocky type and it lack volatiles like light elements like methane, ammonia, water. I mean, I know we have water here on Earth, but not a lot. The percentage of water, which is consists of hydrogen and oxygen. So hydrogen is light, you could call it volatile. So it's not a lot. And the reason for that is when the solar system was formed, the sun's heat evaporates and the sun's radiation, the sun's wind, swept away all these light elements to the regions where the Jovian planets are located. So when you think about the Jovian or gas planets, Jupiter, Saturn, Uranus, and Neptune, they are in a region where the concentration of these volatiles outshine the concentration of rocky type. And when you go to the regions closer to the sun, is somewhat different. So you have more metals and more heavy type of atoms and crystals. There are rocky type crystals closer to the sun than it is further out. So if you look at composition of Mercury and compare that with Mars, which is further out, Mercury has more metals than Mars has. Mars has more silicates than metals. The ratio between those two is different if you compare that with Mercury. And all of that's because of the sun, because of the sun heat. So it seems that the sun, when the sun was formed, it not only controls the dynamics of the solar system, so we know the planets go around the sun following Kepler's law and Newton's law, we know all of that. But in addition to that, the characteristics and the chemical composition of the planets also happen to be controlled and modulated by the sun's influence, if you will. So the sun is not only the creator of its own solar system as a star, but also the one that modulates, that shape, that kind of guide the chemical composition of planets that happen to orbit it. One of the important aspects of chapters 8, Earth as a planet, is plate tectonics. Plate tectonics. And I can't show the simulation because only work for Windows, but I would strongly recommend that you check this plate tectonics best simulation. Is in Fat, Colorado, but I can't run in here unless they improve it and so Windows only, there you go. So I can't do it. It's very, very well done. So you run this simulation. Yeah, if I could. I have a Mac here, so it doesn't go. So you run this simulation, and you can in fact you are faced with the theory of plate tectonics. And what exactly this theory tell us? It tells that Earth is not just a crust, a single crust, but has a lithosphere, a solid surface that is broken in several plates. And these plates have their own independent motion. Some plates, they collide and they move against one another. And as a result of this collision, mountains are formed. So like Himalayas is the result of a collision between Indian plate and Asian plate. Appalachian Mountains is the result of the collision of our North American plate and the Eurasia plate long time ago. Andes is the result of a collision between Nazca plate in South America, which is in the Pacific Ocean, and the South American plate. As a result of this collision, we have a chain of volcanic mountains that's called the Andes. So all of these features are generated because this collision of plates. But not only that, volcanoes also result from these collisions. Oceans are formed because in regions where two plates are diverging from one another, water fills in the gap. And then as these plates move apart one another, water takes the place. And then eventually you have oceans. In other words, our oceans are basically 70,000 kilometers of rift valleys surrounded by mountains that have been generated by this slowly depart of plates in specific areas or regions of our oceans, Pacific, Atlantic, Indian, and you name it. So play with the simulation because it is worth it. It's quite well done, and one of the best that I've seen on this particular subject. And also in association or as a consequence of plate tectonics, earthquakes. So we live in an earthquake zone because we have San Andreas fault and its ramification pretty much passing under our homes and the college, by the way. And we are pretty much aware of the amount of earthquakes that we are subjected to. Now, these earthquakes, when they occur, they generate waves. And these waves are called seismic waves. So there are three types of waves: compressional waves, in which is a uh, push stretch type of waves, like sound waves. And the characteristics of these waves is that they go through solid and liquid material faster than the other type of waves, S waves or shear waves or secondary waves, that moves slower at a slower pace, and they don't go through liquid phase. Because there is a shadowy region where these S waves don't go through, geologists were able to infer the existence of a liquid phase of melted material in the very core of our planet Earth. Okay. And the third type of waves is called surface waves. Those are the most devastated one. They are the most energetic one. They have the largest possible amplitude, and so be away from them. So waves in the oceans, when these waves are generated in subduction zone, they can create tsunami waves, which sometimes we are pretty much aware of their catastrophic um, effects in coastal zones. So pretty much this is chapter 7, is to study planet Earth, its atmosphere, the onset of ozone layer, that is a protective layer of gas, oxygen, primarily 3 atoms of oxygen that blocks UV radiation from arriving the ground. Um, and then we study Earth atmosphere, the Earth surface, and the Earth interior, and this plate tectonic theory, which is the most important one in chapter 7. Okay. Now, chapter 8, what is important in chapter 8 is formation of solar system itself. And now we are pretty much in chapter 14. Chapter 14. So the book has a lot of content, and I have to pick and choose certain sections that can illustrate in general ways what we want to focus in our course. Oh, by the way, this is the idea of how the solar system originated, and I show you an animation on Monday done for a star called EX Lupi, which show exactly, let me see if I can bring this in, this animation again, EX Lupi, which is nicely illustrate how stars are formed. So gas exists out there in the space. Cut the microphone here. Yeah. So, and that's pretty much what it is. You have this gas circulating in a certain direction, and eventually this gas finds its way to the central star, and this gap that exists between the star and the circumstellar disk is in fact controlled by the strong and young magnetosphere these stars are well known to harbor. See if I have another picture of it. Probably not. That is going to be the same. Yeah, it's just a repetition. Um, this might be interesting, but I don't want to see commercial. I just want to see the animation here. Well, that's a good beginning. So we have gas that is circulating in our galactic disk. And in certain regions of this gas, gravity is strong enough, become efficient enough, so that the lady might be saying that collapse takes place. And then gravity slowly but surely will bring the gas to a central point, the center of mass of that system, where a star is going to reside. So you see when this collision, with this contraction takes place, rotation also is part of the game. So you don't have the gas falling like uh, radially or like in a stream is a straight line towards the center. In fact, after this system has evolved sufficiently, the gas falls towards an equatorial plane, and from the equatorial plane, this gas spiral, following Kepler's law, towards the central part. Now, this gas that you see in red here eventually its temperature start to lower down, and then crystals, little particle of dust start to be formed. So and once this particle of dust start to be formed, they will grow in size, mainly because of the same type of physical process that forms snowflakes. So snowflakes is the result of what? You have a little crystals, ice crystals formed in the upper atmosphere, and, and they stick together, attracted by electrostatic forces. So in this gas, in the circumstellar disk, the same process occur, and then these little crystals stick together by a process we call accretion, which is driven by electrostatic forces. But eventually these dust, these grains, they grow in size, and they stick together and they keep on growing to the point that eventually they will be self-gravitating. And now the driving force that bring more material in is not electrostatic force, but it's pretty much gravity force. And this process here is going to show that eventually this particle of dust will grow to the size of being called planetesimals, kilometers and sometimes several kilometers in size. And this bipolar flow that is being shown here, this bipolar flow perpendicular to the disk itself, is the result of conservation of angular momentum, conservation of, if you want to call, rotational energy. And then eventually all these planetesimals will collide among themselves. As they collide, they will coalesce and grow in size, and eventually you are witnessing the formation of a protoplanet. And eventually we have a planet. So that's the origin right there in a beautiful animation, the origins of our solar system, or the origins of any star, as we know of. And line of evidence that support the circumstellar disk, first is that all planets in our solar system, in particular Earth, Mercury, Venus, and the satellites, they all seem to be aligned in the plane that's called the plane of ecliptic. It's not exactly a perfect alignment, but their orbital plane does not differ too much from one another. Okay. So we don't want to think about black holes right now. So let's go to our uh, so what are the objects in our solar system? This was also one of the uh, extra credits that I was putting in one of the chat room. So we have three types of um, bodies or leftovers out there in the space. Some of them fall in our atmosphere. So meteoroids are anything that is not or is not classified as being planet or satellites, or asteroids or comets. So meteoroids are pieces of debris that happen to still exist in around the sun, and some of them enter our atmosphere, and when they enter the atmosphere, they are not necessarily big. They could be the size of a little black beans or the size of a grain of rice, but it can be big as a few centimeters in size or a few inches in size or a few meters in size or even more. And depending on how big they are and the angle in which they enter the atmosphere, the results of their interaction with the atmosphere can be fantastic. Um, when at nighttime, because the sky is dark at night, you might be prone to see these meteors in our atmosphere. So as they enter the atmosphere, they burn out. So friction warm them out, and then you see this nice trace of fire. Sometimes they're called fireballs, sometimes they are called shooting stars. They are not real stars because they are not big, by the way. They are grain of rice, no? So it's not a star. So if a star get close to us, that close, we are dead. We wouldn't even be talking about it. There are other type of shooting star, meteor showers is another term. So meteor showers is the result of what? When comets gets close to the sun's heat vaporize part of the meteor, liberating not only gas but also dust that happen to be embedded in the comet itself body. And as the comet travels through its own path around the sun, it releases this gas and also releases the dust. So it's like a dirty ball that goes around the sun and leaves a trace of particles. So if it happened that Earth goes into this trace of dust, then the atmosphere will be inundated by this dust. And then we see that as meteor showers because all these particles, burning particles in the atmosphere, all these little meteors, if you trace them to a common origin, you might find in which constellations, or in other words, in which region of the sky Earth is going into and colliding or penetrating this trace of dust we call left over by the comet's path. So depending on which the month of the year or which constellation is visible, then the meteor shower will bear the name of that constellation. Okay. Oh, there you go. The meteor shower is right there. Yeah. So in January, we have Quadrantid. It's a constellation, Lyrid in Lyra, April 22nd. Two in Aquarius, Perseus, Orionis. So all these meteor showers represent specific comets associated with it, all comets. And as they pass through the region closer to the sun, they vaporize and they leave a trace of garbage or dust. And if Earth happened to go through that trail, then we see these meteor showers. Now, sometimes these meteors are big enough and able to resist the fall, and they hit ground. If they hit ground and if you collect them, you can make good money on it, but you call it meteorite. So meteorite is a meteor that's survived the fall, and you have a sample of it to tell the story. Okay. Now, meteorites, when you collect them, you are finding they they have different compositions. So some of these meteorites might have a larger concentration of rocky or stony rich meteorite, or they might have a larger concentration of iron, and they are iron rich meteorites. The iron rich meteorites are easier to be found because you can use metal detectors to find them. And the Stony Ridge meteorites are more difficult. You have to have some indication there was a fall, first of all, or you have to use drones to find them in Antarctica in the middle of some depression in the ice, like a little crater, and then you can collect them, or you are trained researcher in the area, and then you can learn to differentiate them from Earth rocks. If they are on the ground for a long time, they might have suffered some weathering and becomes very difficult to differentiate them from any city old rock. So that's why you go to the Antarctica, because the weather pattern and distress is much less than it is, let's say, in Amazon or, or in a non-desert area. Water is a good solvent, it's a good, any chemical reaction is facilitated with the presence of water. So a humid region is more exposed to weathering than a dry region. So you might be able to have a better chance to find meteorites in the desert or in 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 um, in Antarctica. And by the way, they might hit your house too, as you can see right here. If they hit your car, the insurance won't pay for your car, but you can make a good money with the news. That's for sure. So those are the classes that I would like you to have written in your extra credit. So they are here. So a little research would do it. And the formation of solar system, I basically went through those steps before. So we have a guess, right? But this picture here is not a good representation of what happened, because all these four vectors are pointing towards the center. In reality, the way it goes, this original nebulosity or original nebula has some initial rotation, as we say in physics, has some initial angular momentum, has some initial rotation going on. And because of that rotation, this arrow should be more turned towards the equatorial region, perpendicular to the axis of rotation of these giant molecular clouds or molecular region. And but eventually these gases start to collapse. Most of it, more than 90%, goes to the central part, and a small percentage of it, 10% or less, falls towards the circumstellar disk. See, the circumstellar disk here rotates around the star, around the equatorial region of the star, and eventually crystallization takes place, planetesimals are formed, and protoplanets come by. And then you ended up with a system consisting of a star, several planetesimals, and planets. So this illustration here gives you a hint that in the very beginning of our solar system, so if you will, from 4.6 billion years all the way to 3.8 billion years ago, the amount of bombardment in these recently formed planets were fantastic. And in fact, if you look at objects like our moon, like Mercury, objects that are not surrounded by an active atmosphere, objects that don't show plate tectonic, in fact, you still can find the remains of these bombardments in the heavily cratered surface they show. And the more cratered the surface is, the older you can establish that, the history of that particular region. If you look at the moon, for instance, moon, as we studied before, moon has heavily cratered regions called highlands, and has regions that are much smoother called mare. So mare are lava, as the result of lava flow that completely erase most of these heavily craters uh, that were formed during this bombardment area, which indicates that mares are younger surface basically, because it's the result of a lava flow that came earlier, um, in fact came before the formation of these heavy craters. And then eventually you have the sun and the planets, and this obviously is not a scale. All the planets have the same size, and you know that's not the case. But what I would like to call your attention for is that in the region closer to the sun, you have metal oxides primarily, and as you go away from the sun, the percentage of these metal oxides fall down, and then you replace them with some silicates. And they are kind of absent in its majority when you go to the uh, gas-like planets. Those they are primarily formed with volatiles. So Jupiter, Saturn, Uranus, and Neptune, they do have rocky material, but it's sink down to their very core. And this bombardment is so significant and so important to explain the origins of our solar system that here comes the extra credit that I would like you to work on, and I will upload a um, a, a question by the end of today, or perhaps tomorrow morning if I have more time. Is based on an ANEW that came today here, space.com. It's right here. So you go to space.com. In the first page you have this nice, no, I already aimed. No, I don't want to do this. Get away, get away. No, it's not the, no, wait a second. There you go. Something big crashed into Uranus and changed it forever. So this article here, it tells or attempts to explain why Uranus is tilted with respect to the other planets. So what has caused this tilt? Like Venus, for instance, if you look at Venus, Venus rotates on its axis of rotation in a direction that's completely different from all the other planets. So if you look at what is this advertisement? Feeling good, tease.com. You got to be kidding. No, should I have it? This advertisement has nothing to do with astronomy. There you go. And how about this? More cash back earned. I don't care for that. I have to talk to the space.com people. But anyways, or Google maybe. So why Uranus is tilted? Why Venus? If you were standing in Venus' surface and you could see through its clouds, we wouldn't see the sun rising in the eastern sky and set in the western sky as we saw, as we see here on Earth, and as we studied previously in our chapter 2. But if you were in Mars, or in Venus, I mean, you would, and you could see through the clouds, the sun would rise in the western sky and set in the eastern sky, because Venus goes in the opposite direction as a result of collision. So what you need to do is to read this article here, and which is very short, right? It's very short, and then you can answer the question that I will ask, which is very simple. Okay, that's the extra credit. I will upload the question um, as soon as I finish this talk, or maybe tomorrow morning if I have to do something else. And let me save the the link here. Okay, so this is pretty much our conversation today. And I wonder if you guys have any question. Charles is there, Charles Nguyen, and Jessica is still there. So Jessica, now you know what is the extra credit you asked today?
Yeah, so
Yeah, I will upload it. You
you're gonna
just
ask the question later, right?
yeah. Tomorrow you can do it, and I will have it available up to Sunday, so you have some time.
Oh, okay.
All right.
Perfect. I'll try to do that when as soon as you post it.
Okay, sounds good. Charles, do you have any question? Let me stop taping so I can